Hello everyone, myself Assistant Professor Vatsal Patel from Civil Engineering Department working at Mahatma Gandhi Institute of Technical Education and Research Center NAVSARI. Today we are going to discuss about geodetic surveying and our today's topic is station marks and signals. So be ready with your pen and paper. So, when selecting triangulation stations, the surveyor should bear in mind the following considerations like stations should be intervisible. For this purpose, stations are placed on the highest point of the elevated ground such as hilltops, housetops, etc. Station should form well-conditioned triangles. In general, no angle should be less than 30 degree or more than 120 degree. As far as possible, the triangles should be isosceles with base angles of about 56 degree or they should be equilateral triangles. Next, the station should be easily accessible. Supplies of food and water should be available. There should be a suitable place for camping or nearest suitable accommodation is available. Station should be so selected that the survey lines are not too long. Small sites lead to inaccurate centering while long ones cause inaccurate bisection of the signal. Station should be so selected that the cost of clearing, cutting trees and erecting towers is minimum. Next, station should be in commanding positions so as to serve as control for subsidiary triangulation or detailed surveys inside the network. Station should be selected so that the line of sight do not pass overcrowded localities such as cities, town, factories, etc. to avoid irregular atmospheric refraction. The line of sight should not graze ground or other obstruction. It should pass at least 2 to 3 meters above the ground. So let's see the intervisibility of triangulation stations. The most essential condition of triangulation is that the stations should be intervisibility. As stated earlier, the station should be chosen on high ground so that they are intervisible. For small distances, intervisibility can be ascertained during recognitions by direct observation with the help of powerful binoculars either at ground level or from the tops of trees. If the distance between the stations is too large or the difference in the elevation between the station is less, then the stations are not intervisible. To ascertain intervisibility, it is necessary to raise both the instrument as well as the signal to overcome the curvature of the earth and to clear all the intervening obstructions. The calculations of the heights of a signal as well as that of an instrument are necessary to determine whether it is necessary to elevate the stations to get the intervisibility or not. So let's see the station marks. The exact positions of the triangulation station should be permanently marked so that the theodolite and signal can be centered accurately over them. The object of station mark is to provide a surface mark with a permanent mark buried below and a good target. Depending upon the nature and purpose of triangulation, stations are fixed and they are permanently marked. It should also include a complete description to enable the station to be recovered even after many years. Each station is also identified by local reference marks, which are permanent features of that area. The marking is done on a copper or brass tablet with the station identification clearly marked. The name of station and the year in which it is set should be stamped on the tablet. So the following points should be considered while marking the exact position. So let's see. So first one is the marks should be distinctive and indestructible. The station should be marked on a perfectly stable foundation or rock. If the size of rock is so large, the station mark on such large rock is generally preferred so that the theodolite and surveyor can stand on it. Next, generally a hole 10 to 15 centimeter deep is drilled into the rock and a copper or iron bolt is fixed in the hole in cement mortar. In some area, if rock is not available, a large stone is embedded about 1 meter deep into the ground. A circle and a dot are cut on it. A second stone with a circle and a dot is placed vertically above the first stone. A GI pipe or say galvanized iron pipe about 25 cm diameter driven vertically into the ground up to a depth of 1 meter can also serve as a station mark. So the mark may be set on a concrete monument also. The station should be marked with a bronze or copper tablet. The name of the station and the date on which it was set should be stamped on the tablet. So here you can see the arrangement of it in the figure. So in earth generally two marks are set. One about 75 centimeter below the surface of the ground and the other extending a few centimeters above the surface of the ground. The underground mark may consist of a stone with a copper bolt in the center or a concrete monument with a tablet mark set on it. So you can see real life image of it. So the station mark with a vertical pole placed centrally should be covered with a conical heap of stones placed symmetrically. The arrangement of marking a station is known as placing a crane. 2 or 3 reference marks similar in material and shape to the station mark should be provided around the station mark. The distances and bearings of these reference marks from the station mark and from each other should be recorded on them. If station is disturbed, it is re-established by using these reference marks. Next, surrounding the station mark, a platform of 3 meter by 3 meter by 0.5 meter should be built up of earth. It provides rigid support for the instrument and the signal. At each station where a tall signal tower is required, an azimuth mark should be established at some distance away from the station mark. It should be of the same size and character as the reference mark. Next is signals. So they are devices erected to define the exact position of an observed station. Signals are used to define the exact position of triangulation station during observation from other station. Signals are centered vertically over the station mark. The accuracy of triangulation depends to a large extent on the proper centering of the signals. Therefore, it is very essential that the signals are truly vertical and centered exactly over the station mark. So, signal should satisfy the following requirements. It should be conspicuous. For example, clearly visible against any background. It should be capable of being accurately centered over the station mark. It should be of suitable size for accurate bisection. It should be from phase or it should exhibit little phase. It should be symmetrical and easy to erect in minimum time. It should carry a flag on its top. Next, signals can be classified into three types. First one is daylight or opaque or say non-luminous signals. Second one is luminous signals and third one is night signals. This theory is very important for your examination, so be sure you remember it with the figure also, because a neat sketch should be also drawn when writing this theory. Okay, so let's see. So first one is opaque signal or say non-luminous signals. These are used for triangulation with less accuracy and for sites not exceeding 30 km. They are used during daytime observations. They consist of various forms of poles, masts and targets. So next is pole signal. If pole is used when the angle of measurement at the station is not required and the sites are less than 6 km. It consists of a round pole pointed black and white in alternate strips. It is supported vertically over the station mark, generally on a tripod or quadripod. So you can see its image here. Next is target signal. A target signal consists of a pole carrying two square or rectangular targets placed at right angles to each other. The targets are generally made of cloth stretched on wooden frames. Target signal is suitable up to a distance of 30 km. So you can see its image here. Next is pole and brush signal. It consists of a straight pole about 2.5 meter long with a bunch of long grass tied symmetrically around its top to form a cross shape. The signal is erected vertically over the station mark by heaping a pile of stones up to 1.7 meter round the pole. A coat of whitewash is applied to the signal to make it conspicuous. So you can see its image here. Next is stone crane. A heap of stone is placed around the base. A stone crane is a conical heap of stones about 3 meter high. A cross-shaped signal is erected over the stone heap. So you can see its image here. And the last one is beacon. It consists of red and white cloth tied around the three straight poles. This can be easily centered over the station mark. It is very useful for making simultaneous observations. So you can see its image here. So if we talk about it, to make the signal conspicuous, a flag tied to the top of the signal. The diameter of the signal is about 1.3 d to 1.9 d into centimeter, where capital D is the distance in kilometer. The height of the signal is about 13.3 d in centimeter. The vertical angle to the signal being at least 30 degree. The signal should be dark in color for visibility against the sky. In general, opaque signals are cheaper than luminous signals and are used for distances. Next is luminous signals. Luminous signals are also known as sun signals, as they are based upon the reflection of sun's rays from a mirror. Such signals can be used only in daytime when the weather is clear. They can be used for long distances. For geodetic work, it is general practice to make observations on luminous signals. These have the advantage of distinct and clear visibility even for long distances or say more than 30 km. Next is heliotrope. A heliotrope essentially consists of a plane mirror for reflecting the sun's rays and a line of sight to direct the reflected rays towards the observer. Heliotrope may be simply a sight vane with an aperture and crosshairs, or it may be telescopic. So here you can see its image. Here is the simple heliotrope and here is the telescopic heliotrope. So if we talk about it, there is a small hole at the center of the mirror and a side vane is an aperture carrying crosshairs. The line of sight passes from the mirror hole to the center of the crosshair. The circular mirror can be rotated horizontally as well as vertically through 360 degree. The heliotrope is centered over the station mark and the line of sight is directed towards the station of observation. Flashes are sent from the observing station to establish the line of sight. The mirror should be adjusted every few minutes since the direction of the sun goes on changing. A form of heliotrope is the Galton sun signal used for lines of sight exceeding 30 km. A telescope is sometimes used instead of the sight vane to form a telescope line of sight. The best time for observation with Helios is towards sunset. The heliotrope reflects a continuous beam of light, whereas a heliograph reflects periodic beams. So the following points should be noted that the heliotropes do not give better results compared to the opaque signals. These are useful when the signal station is in flat plane and the station of observation is on elevated ground. When the distance between the station exceeds 30 km, the heliotropes become very useful. These are very cheap and have no running and operating cost. But use of these signals for the first order triangulation is restricted since it can be used on sunny days only. Next is night signals. When the observations are required to be made at night, the night signals may be used. So various types of night signals are there, like various forms of oil lamps with parabolic reflectors for sights less than 80 km. Acetylene lamps designed by Captain G.T. McCaw for sights more than 80 km. Magnesium lamps with parabolic reflectors are used for long sights. Some types electric lamps are also used. Next is towers and scaffolds. A tower is erected when it is desired to elevate the instrument or signal above the triangulation station to obtain a line of sight clear of obstructions. Tower is a temporary structure constructed for the purpose of surveying to elevate instrument and signals. The height of tower depends upon the character of the terrain and the length of sight. So the structure actually consists of two towers, one inside and other outside. So here you can see its image here. Inside tower is there, outside tower is there, screen, lamp, windows are there. It is known as the Biblis tower. So the inner superstructure supports the instrument only, whereas the outer structure supports the observer and the signal. This is done to avoid any disturbances to the towers due to the movement of the survey party. The two towers may be made of masonry, timber or steel. For small heights, masonry towers are most suitable. Timber scaffolds are most commonly used and have been constructed to heights over 50 meter. For greater heights, steel towers are commonly used. Steel towers made of light sections are very portable and can be easily erected and dismantled and transported. Bilby's towers, patented by J.S. Bilby of the U.S. Coast and Geodetic Survey, are popular for heights ranging from 30 to 40 meter, with a beacon 3 meter higher. 5% can erect this tower weighing about 3 tons in just 5 hours. Next is scaffolds. For first order and second order triangulation, occasionally the scaffolds are used across plane. They are portable and may be made with steel or timber. These are used for small heights, generally 10 to 15 meter. The scaffolds are also made with a double structure similar to towers. The two towers should be entirely independent of each other so that the movement of the observer does not disturb the instrument. So here are some important questions which can be asked in your examination. So be sure you read each and every one of these. Okay, and mainly the station marks are very important. So here I end my session. Thank you all of you.